Now, we all know that water is called the universal solvent because it's very good at dissolving a lot of different types of compounds. We also use quite frequently a phrase called like dissolves like. And you guys hopefully should know that that means that anything that is polar will dissolve in other polar solvents, and anything that is nonpolar should dissolve in a nonpolar solvent. Well, it's not quite that easy. It's a little more complicated. And what we're going to talk about today are the rules that basically dictate what will dissolve in water and what will not. What we're going to need is our formula chart. This is my periodic table. I'm going to flip it over, and right here in the center are the solubility rules, which you can see on the left side of your screen. So the way this works is you'll notice at the top of this chart here, we have a section at the top called soluble and a section down here for everything that is insoluble. Again, it's shown right there. So what we want to do when we're trying to figure out what is soluble or insoluble in water is we're going to look at the right side of the compound. In this case, notice the chlorine. So we're going to look for the chlorine, not the sodium, just the chlorine. So I'm going to go to my left side of my screen. I'm going to scan down until I find chlorine, and there it is. So notice it's in the top box. That means it should be soluble. So anything with a chloride should be soluble, but there are some exceptions. The exceptions for chlorine are anything, a chloride that is bound to silver, lead, or mercury. So now I go back to the first half of my compound and I notice that it's bound to a sodium. Sodium is not silver, lead, or mercury. So that means the exception does not matter because it is not an exception. Therefore, it will remain soluble. It will stay soluble. So I'm going to put an S, a funny looking S, for soluble for sodium chloride. Okay. Let's try the next one again. So what we're going to do exactly like the last time is look at the right side of the compound. In this case, it's chlorine again. So there's my chloride again, still in the soluble section. Now I need to look at the exceptions. This time it's bound to silver. Silver is one of the exceptions. Therefore, it would become the opposite. It is no longer soluble. It is now going to be insoluble. All right, the next one is going to be sodium phosphate. So I'm going to look at the right side of the compound. In this case, phosphate. I'm starting at the top. I'm going to scan down all the way until I find phosphate. There it is. It's in the bottom section. In the insoluble section, I'm going to look at what exceptions it has. It should be insoluble. It should not dissolve in water unless it has a compound of ammonium, which is NH4, or any of the alkali metal cations. Alkali metal cations, a lot of people forget what that is because we learned that so long ago, but an alkali metal cation is anything in the first column. Anything in the first column is an alkali metal. So back to the problem, PO4 should be insoluble unless it is bound to sodium, which it's not. Ammonium, or any of the group 1 metals. Now, sodium is located right there. Sodium is a group 1 metal. Therefore, it is an exception. It will no longer be insoluble. It makes it the opposite, which is now going to be soluble. If sodium was not there, it would stay insoluble. Okay, next one. We have copper 2 hydroxide. Copper 2 hydroxide. So again, you guys know, we'll look at the OH. Find OH. It's down here near the very bottom. It's in the insoluble section. It's bound to copper, and the exceptions for hydroxide are compounds of ammonium, any of the alkali metal cations, calcium, strontium, or barium. So it's definitely, copper is definitely not ammonium, calcium, strontium, or barium, but is copper a group 1 metal? And no, it's not, because copper is located somewhere way over here, not here. So therefore, it is not one of the exceptions. So the hydroxide will make it insoluble. It will not dissolve. All right, let's do a few more of these. I'll do 4 more with you. So next is ammonium hydroxide. So hydroxide is, again, still right here. Its exceptions, are ammonium, alkali metal cations, calcium, strontium, and barium. Well, we have ammonium. Because ammonium is the exception, it is no longer insoluble. That makes it the opposite, which makes it soluble. So you see how this works, guys? Aluminum sulfate. So sulfate is located right up here. Its exceptions are strontium, barium, lead, and mercury. Aluminum is not one of the exceptions, so that will keep it where it belongs, which is soluble. Again, if aluminum was one of the exceptions, it would make it the opposite, which is insoluble. Next, we have magnesium carbonate. So carbonate, I'm looking for it. Somewhere in the top, I thought. Oh, no, it's in the bottom. There it is. Carbonate's the very first one. So its exceptions are ammonium and anything in the very first column called the alkali metal cations. So magnesium is on the left side of the periodic table, but it's in a group 2. Magnesium is a group 2 metal. The alkaline earth metal is not an alkali metal cation. Therefore, it will remain insoluble. Okay, the next thing we have is lead 2 sulfide, PBS. So S is all the way down there in the insoluble section. Its exceptions are ammonium, alkali metal cations, calcium, strontium, and barium. What we have over here is it's bound to lead. Lead is not one of those exceptions, so it will remain insoluble. All right, guys, again, that's basically how the solubility rules work, excuse me. You look at the right side of the compound, you just see, is it in the top section, which is soluble, or the bottom section, which is insoluble? Then you look at the exceptions, see what the first metal is on your compound of interest. And if it is an exception, it makes it the opposite. If it is not an exception, then it stays what it is. All right, guys, as always, thanks for watching, and I hope you enjoyed.